Hi, everybody. This is Mr. Karlovsky, and we're going to continue with our notes for the second part of 9.4. And I have these pictures on the screen. These sweatshirts were very popular a while ago. I don't see them much around the hallways anymore. Basically, this is just the letters GBS, but they're Greek capital letter counterparts, gamma, beta, and sigma. And so I just wanted to show you these sweatshirts if you've seen them before, if any of your siblings have them. But yeah, I don't see them in the bookstore much anymore. But the reason I showed them to you is because this second part is about that Greek letter sigma. So we're going to talk about sigma notation. And yeah, it's that Greek letter. I draw it kind of very jagged like this, kind of a bunch of straight lines and angles. But yeah, so that's a symbol that we use in mathematics to represent addition. It's kind of a way of saying, hey, add them up. What's the them? We'll find out. But hey, add up a bunch of numbers. So I'm going to start with just an example of showing you the notation and kind of working backwards. So there would be this Greek capital letter sigma. Below it, it might say n equals 1. On top, it might say the number 5. And then to the right side, there might be a expression like 3n plus 1. And so, yeah, this is a notation about how to read this and understand it and what does it mean. And all it says, it's probably what you might guess it says, is that, hey, here's an expression or a formula, if you want to call it, 3n plus 1. And this says, hey, plug in the n values from 1, 2, and through 5. So we're going to plug in 1, 2, 3, 4, and 5. So it's kind of a start and stop. Plug in all the numbers, so get those 5 terms, and then the sigma tells us to add them up. That's literally all it is. So if I were to squeeze it in, we'd have 3 times 1 plus 1 plus 3 times 2 plus 1 plus 3 times 3 plus 1 plus 3 times 4 plus 1 plus 3 times 5 plus 1. So that's what that instruction means. And of course, we could go to our calculator or maybe do these in our head, but go to our calculator, type in those expressions, and we would just add it up, and we're going to get the number 50. If you want to check my work, there you go. Okay, so that's really all we want to talk about is today is the notation. Okay, so to kind of generalize that notation, if I could do that for you. So you got this Greek capital letter sigma. So you say n equals, and then you're going to put the start term, and I'm going to say position, because it's not the actual term, it's just the term position. Maybe you start with term number 1, maybe you start with term number 7, but what's your start term position? And then on top, you will put the end term position. And then to the side, the key thing is that it has to be an explicit formula. Okay, you might be tempted to think about using recursive, but it has to be an explicit formula. And that's it. So first we're just going to practice how to read this expression. So we're going to do a bunch of them here. I'm going to jump ahead. Boom. So now it says, that says, hey, add up terms 1 through 4 of this formula. So first off, I want to show you, it doesn't have to be arithmetic or geometric. It could be any formula, any explicit formula to the right side. So we're going to plug in 1, 2, 3, and 4. And I'm just going to do these in my head. 1 squared minus 1 is 0. Plus, if I do 2 squared minus 2, that's 2. If I plug in 3 squared minus 3, that's 6. And if I plug in 4 squared minus 4, that's 12. Add it all up, and I get a number. And that's the important thing, that these are just expressions that, if they have numbers to plug in, your answer will be a number. All right, let's do another one. Okay, and this one says add up the terms 8 through 11. So you don't have to start with term number 1. I would say it's nice when you start with term number 1, but you don't have to. Just from term 1, or sorry, in this case, from term 8 to 11. So 8, 9, 10, and 11. That's all we're going to do. We're going to plug in 8. So it's really kind of instructions. Hey, plug in 8, you get 3 halves. Plug in 9, you get 3 thirds. Plug in 10, you get 3 fourths. Plug in 11, you get 3 fifths. Those are not terribly fun to do, no calculator, so I'll go to my calculator and get 77 over 20. Okay, so again, it's just a way of to add up a bunch of stuff without having to write it out. And that's really where, the notation is very helpful, is that this is a way that you could write down, add up a lot of numbers in a very small amount of space. Okay, now as far as calculating it, we know that sometimes we have formulas or other patterns, but for now we're just practicing the reading and writing. And in fact, that's what my next example is going to be. Okay, it says write the sigma notation for that sum. Okay, I mean, that's just six numbers added together. We can obviously go to our calculator, but just to practice how to write the sigma notation for that expression. Now, let's start with, okay, we're supposed to write a capital letter sigma. Now, I see that there are 1, 2, 3, 4, 5, 6 numbers, so it would make a lot of sense for me to choose to let me to plug in 1 through 6. I mean, I could do 2 through 7, but I don't know why I would make that choice. If I've got 6 numbers, let's just go 1 through 6. So now we have to figure out what's the formula of this sequence. So either it's got to be something that's really obvious or something we know. And if you look at this pattern, 22, 31, 90, 40, 49, 58, and 67, the pattern is that it's adding 9, but that's where kids make mistakes. They'll start to write like 9n or something like that. No, no, no. Yes, 9 is an important part of the pattern, but you have to make the connection that this is arithmetic. And so if we need a formula for an arithmetic sequence, we should know how to do that, that the nth term of this arithmetic sequence would be the first term 22 plus the d value of 9, n minus 1. So again, you don't have to write this to the side. In fact, this is what you're going to write in the formula, that the sigma of the expression 22 plus 9, n minus 1. Okay, so that would be your answer to write the sigma expression for that problem. Okay, all right, let's do one more of the writing the sigma expression. So here, 25 plus 36 plus 49 plus 64 plus 81. Let's write the sigma expression. And so again, I kind of just immediately write my sigma. All right, now, out of force of habit, I might think that there are 1, 2, 3, 4, 5 problems, or have 1, 2, 3, 4, 5 numbers. So I will do n equals 1 to 5. And we can do that. However, did you look at these numbers? 25, 36, 49, 64, and 81. If we want to, oh, is that arithmetic? No, because that's plus 11 then plus 13. Okay, it's not arithmetic. Is it geometric? Is there a multiplier? And I'll tell you, no, there's not a constant multiplier. Instead, did you realize that these are just the perfect squares? Those are perfect squares. So this is where I'm going to show you, you could have multiple answers. To me, I might recognize that the pattern is literally just n squared. Take a number and square it. However, if I see it that way, then my first term is not term 1. My first term would be term 5. And my last term would not be, 5. It would be the ninth term, so from 9. All right, so that could be one way to do the answer. However, if you're on the left side and you're like, no, I want to just plug in 1, 2, 3, 4, 5, well, then you just have to figure out the adjustment. And for this one, how do I plug in 1 and make it do 5 squared? How do I plug in 2 and make it do 6 squared? Hopefully you can think about that one. That would just be n plus 4 squared, right? That would work. Plug in 1, you get 5 squared. Plug in 2, if you plug in 5, you get 9 squared. And so that would work. So sometimes, in fact, almost all the time, there's definitely more than one way to write it. It's up to you whether you prefer to start plugging in 1 or if you want to do the easier formula. It's up to you. All right, just a few more examples, we'll be done. All right, we're back to reading of an expression. Hey, this says add up all the terms from term 1 to term 75 of the expression 5 minus 2n. And at first glance, you might say, this is impossible. He wants us to add up 75 numbers. How dare he? Well, if I plug in 1, I would get 3. If I plug in 2, I would get 1. If I plug in 3, I would get negative 1. 4 would get me negative 3. And I could keep on going, but I don't want to do that 75 times. So in this case, even though this is sigma notation, I would hope that you would say hey, wait a second, we just did this the other day. This is an arithmetic series, right? This is asking us to add up terms of an arithmetic sequence, right? 3, 1, -1, -3. So this is an example where even though it's a sigma notation problem, we don't have to do sigma notation. We can go, hey, I have a formula for the sum of 75 terms of an arithmetic sequence. Do you remember it? This is the arithmetic one. This is the n over 2. So 75 over 2. And all I need is the first term, which I guess we already found by plugging in. We got 3 plus, and then the last term, well, we haven't found it yet, but since I know my last term is 75, I can just plug in 75 and get negative 145. And there we go. So again, I know I'm doing these fast with the formulas, but just the idea that although sigma is cool and sigma works for any problem, if you can recognize that, hey, this is arithmetic or hint, hint, geometric in a moment, if you can know that, then maybe instead of using sigma, we can use those formulas that we've spent the last couple classes on. All right, just a couple more examples. Okay, this one says add up terms 1 through 10 of this formula, 12 times -2 to the n minus 1. Now this one, I don't even want to bother writing out terms because this one, I can just use my eyes and say, hey, this is geometric. Okay, so that, that fits our structure. So this is a geometric sequence. So therefore, this is a geometric series. Okay, and again, how do I know that? That fits our structure of a sub 1 times r to the n minus 1. I don't need to figure it out. It's right there for me. So we have a formula for that. The sum of 10 numbers of a geometric sequence is the first term 12, right? Wait, what is it? Yeah, that's the first term right here. 1 minus, and then I made the point before, r should be in parentheses, -2 to the 10th, all over 1 minus -2. And that's a formula. So again, this one, you should not take your time plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You recognize it's geometric, recognize we have a formula, and we plug that in, and you should get negative 4,092. And one final example. I'll just scroll up here. Final example related to the previous video. So if you watch these videos out of order, you're not going to understand this. So now what if I say, hey, let's add up terms 1 to infinity, right? It's weird to let infinity be in the place of a number. But if I do terms 1 to infinity of 2 times 3/5 to the n minus 1, and we'd say, again, we'd just kind of, these are all check boxes in our head. Hey, this is geometric. Hey, this is infinite. And we saw in that previous video that it only works if r is less than 1, which it is. So therefore we go, hey, I don't need to do any more thinking. I can just go right to my infinite series formula, s sub infinity of a sub 1. A sub 1 would be 2 over 1 minus the r value of 3/5, and that is actually a very nice number of 5. Okay, so this is all about reading the expressions. Sometimes we write it out. Sometimes we have to write it out. If it's not arithmetic or geometric, we have to figure out something else. Okay, so that's kind of, this almost wraps up the entire chapter. We'll do a little bit more review next class. But yeah, we've done arithmetic and geometric, but for additions of problems that of sequences we don't know, we could use sigma notation. All right, I know this was a lot, and hopefully this is the last Easter egg for you. Did you notice at the very beginning, who is that on the left? That is choir director Mr. Robbie Shellard when he was a GBS student in 2009. No, I did not have this picture. He sent it to me because I asked for a picture of the sweatshirt. He had that. Anywho, oh, Mr. Shellard. All right. Have a good day, and I hope these videos made sense and your homework will be all good. All right, take care.